What China found at the bottom of the Mariana Trench will terrify you and completely change how you see life in the universe. You already know the Mariana Trench is deep, but deep doesn't even begin to cover it. We're talking nearly 11,000 meters. That's deeper than Mount Everest is tall. You heard that right. If you dropped the highest mountain on Earth into the Mariana Trench, its peak would still be submerged under more than a mile of ocean. China sent humans down there, repeatedly, systematically. And what they brought back didn't just make headlines, it rewrote science. And the deeper you go into what they found, the harder it is to look at our world the same way again, starting from zero. Picture this. It's the year 2001, and the most powerful navies and research institutions on Earth have spent decades quietly mapping the ocean floor, sending submersibles into the deep, and planting their flags at the bottom of the world. The United States had already sent the Trieste down to Challenger Deep back in 1960. Japan had built Kaiko, an unmanned vehicle that touched the very bottom. France, Russia, they all had deep-sea programs with decades of experience behind them. China had nothing. Not a submersible. Not the engineering infrastructure to build one. Not the trained personnel to operate one. When it came to the deep ocean, China was starting from absolute zero, and everyone in the scientific community knew it. But here's what most people don't realize. That wasn't an accident of history. It was a gap China had consciously decided to close and close fast. In the early 2000s, China's leadership made a decision that would take 20 years to fully pay off. They identified deep-sea exploration as a national priority not just for scientific prestige, but because they understood something that most governments hadn't fully articulated yet. Whoever understood the deep ocean would have an edge, scientifically, strategically, and ultimately, in the race to understand life itself. The ocean floor holds untouched mineral deposits, unknown biological compounds, and answers to questions humanity hasn't even thought to ask yet. China wanted all of it. So they started building. And this is where the story gets interesting, because what China was attempting wasn't just technically difficult, it was a different category of hard. Building a vehicle that can survive nearly 11,000 meters of descent means engineering something to withstand pressure of over 15,000 pounds per square inch. That's roughly 1,000 times the atmospheric pressure you feel standing outside right now. At that depth, water doesn't just surround the vehicle, it tries to crush it out of existence. Every seal, every viewport, every electrical connection becomes a potential catastrophic failure point. One miscalculation, one microscopic flaw in the hull, and the submersible and anyone inside it is gone. No margin for error, no rescue mission, no second chances. The engineers, tasked with building China's first serious deep-sea submersible, were working with borrowed knowledge, reverse-engineered principles, and a timeline that made Western experts quietly skeptical. The project was called Jiaolong, named after a mythical Chinese dragon said to rule the seas. And the name wasn't chosen casually. This was a statement of intent. But intention and execution are two very different things. The early years of the Jiaolong program were defined by failure, redesign, and the kind of grinding technical setbacks that never make it into the final press release. Pressure hull tolerances that didn't hold. Buoyancy systems that behaved unpredictably. Communication blackouts during test dives that sent engineers scrambling. Every problem solved revealed 3 more waiting underneath it. For a program built on national pride, the slow crawl of progress was its own kind of pressure. Then came the moment everything changed. In 2012, Jiaolong descended to 7,062 meters in the Mariana Trench, a world record for a crewed submersible at the time, and a moment that landed like a shockwave in the global deep-sea community. China hadn't just caught up, it had announced itself. After a decade of doubt and quiet persistence, the Dragon had reached the deep, but 7,000 meters wasn't the bottom. And China knew it. Jiaolong could dive deep, but it couldn't reach Challenger Deep, the absolute lowest point on Earth's surface, sitting at nearly 11,000 meters. To go all the way to the bottom, China would need something it didn't have yet, something more capable, more durable, and more sophisticated than anything it had ever built. The program that started from zero had proven it could compete. Now it had to prove it could win. And what China built next would make Jiaolong look like a prototype. 3 generations, 1 goal. Jiaolong had proven China could build a deep-sea submersible. But the engineers who built it knew something the headlines didn't say out loud. 7,000 meters was impressive, and 11,000 meters was a completely different world. The gap between those two numbers isn't just distance, it's physics. Every additional meter of descent adds pressure, compounds engineering stress, and shrinks the margin between a functioning vehicle and a crushed one. Going from 7,000 to 11,000 meters meant redesigning almost everything from scratch. The hull material, the pressure compensation systems, the viewport geometry, the syntactic foam used for buoyancy. Jiaolong had been a proof of concept. What China needed now was a machine built for the absolute limit. So they built one. They called it Shenhai Yongxi, the Deep Sea Warrior. Shenhai Yongxi represented China's second generation, a submersible that could push past Jiaolong's ceiling and operate in depths closer to the full ocean floor. It carried more sophisticated scientific instruments, improved life support systems, and a hull engineered to survive pressures that would flatten a conventional steel container like a tin can. It was faster to deploy, more stable in descent, and more capable of collecting samples without disturbing the fragile sediment layers that held millions of years of biological history. But it still wasn't enough. And this is the part that most people gloss over, because building 3 successive generations of deep-sea submersibles in under 2 decades isn't just an engineering achievement. It's a statement about national patience. Most countries with deep-sea ambitions built one vehicle, celebrated it, and moved on. China treated each submersible as a stepping stone, a deliberate iteration in a longer plan that was always pointed at one destination: Challenger Deep. The 3rd generation was called Fendouzhe, which translates to striver. And the name fits, because what Fendouzhe was designed to do had never been done before, not by any nation, not with any vehicle. It wasn't built just to touch the bottom of Challenger Deep. It was built to work there, to stay, to collect, to run systematic scientific missions at a depth of nearly 11,000 meters, repeatedly, over time. In November of 2020, Fendouzhe descended to 10,909 meters, the deepest crewed dive in history by a Chinese submersible, placing it firmly at the floor of Challenger Deep. But the record wasn't the point. What happened after the record is what matters. China didn't plant a flag and go home. They went back, again and again. Fendouzhe completed multiple dives to full ocean depth, each time carrying scientists, not just pilots, down to the bottom to conduct real research in real time. This is the part that separates China's program from everything that came before it. Earlier expeditions to Challenger Deep were monumental achievements, but they were brief. Touch the bottom, collect what you can, ascend. The science was limited by time and by the vehicle's capability. Fendouzhe changed that equation entirely. With a crew cabin large enough for 3 people, a suite of robotic arms, water samplers, sediment corers, and high-definition cameras, it turned Challenger Deep from an unreachable destination into a functioning research site. For the first time in history, scientists could sit at the bottom of the world and actually do their jobs. And this is where the story stops being about engineering and starts being about what they found. Because the scientists who descended in Fendouzhe weren't just collecting samples to bring back to a lab and study over months and years. They were watching, in real time, as the lights of the submersible illuminated a world that had never been seen clearly before. A world where everything science assumed about the limits of life was about to be proven wrong. What was living down there, and how it was living, wasn't just surprising. It was the kind of discovery that makes you question everything you thought you understood about where life can exist and what life actually needs to survive. And China had 1,600 samples to prove it. What they pulled up: 1,600 sediment samples. That's what China's deep-sea missions brought back from Challenger Deep. Not water samples, not rock fragments. Sediment, the ancient, compressed biological record of the ocean floor. Each layer holding millions of years of microbial history packed into a few inches of dark, freezing mud. When scientists began analyzing those samples, they expected to find life. What they did not expect was the scale of it. 7,000 microbial species, living, reproducing, and thriving at nearly 11,000 meters below the surface, in total darkness, under pressure that would kill a human being instantaneously, in water that hovers just above freezing. 7,000 species, and 89% of them were entirely unknown to science. You heard that right. Almost 9 out of every 10 living organisms pulled from the deepest place on Earth had never been seen before, never been named, never been studied. They existed in a world science had barely visited, doing something science said shouldn't be possible. And that's where the real story begins. For most of human history, the assumption was simple life needs sunlight. Sunlight drives photosynthesis. Photosynthesis produces energy. Energy sustains ecosystems. The entire food chain, from the smallest plant to the largest predator, traces back to the sun. It was one of biology's foundational rules, so deeply embedded in scientific thinking that questioning it felt almost pointless. The Mariana Trench broke that rule completely. At 11,000 meters, no sunlight reaches the ocean floor. None. The darkness down there is absolute, the kind of darkness that has existed, uninterrupted, for millions of years. And yet the sediment samples China brought back weren't just carrying dormant microbes clinging to survival. They were carrying evidence of entire ecosystems complex, layered, interconnected biological communities operating on a completely different energy source. Chemosynthesis. Instead of sunlight, these organisms harvest energy from chemical reactions, specifically from hydrogen sulfide and methane seeping up through cracks in the ocean floor. Bacteria consume these chemicals and produce energy, and that energy flows upward through the ecosystem, just like sunlight flows through one on the surface. Around hydrothermal vents and cold seeps on the Mariana floor, China's submersibles captured footage of tube worms stretching several feet long, clusters of pale clams, shrimp, and other organisms gathered around these chemical vents in dense, thriving communities. No sunlight, no photosynthesis, no connection to the surface world whatsoever. Just chemistry, darkness, and life finding a way. But this wasn't just biologically remarkable. It was philosophically shattering. Because if life doesn't need sunlight, if life can build entire ecosystems from chemical energy alone, in crushing pressure, in near-freezing temperatures, in total darkness, then every assumption science has made about where life can exist needs to be reconsidered from the ground up. And the scientists analyzing China's samples understood exactly what they were looking at. The microbes recovered from Challenger Deep sediment weren't just surviving extreme conditions, they were optimized for them. Their cellular membranes were chemically adapted to function under pressures that would rupture normal cell walls. Their metabolic processes were fine-tuned to extract maximum energy from minimal chemical input. These weren't organisms accidentally clinging to existence at the edge of viability. These were organisms that had evolved over millions of years to call this environment home, and they were thriving. Some of the newly discovered species carry genetic sequences unlike anything in the global biological database, entirely novel protein structures, metabolic pathways that don't exist anywhere else on Earth. Biological machinery is so unfamiliar that researchers are still working to understand what it does and how it evolved. Each new species is essentially a new chapter in the story of what life is capable of, and China's samples added nearly 6,000 new chapters in a single research program. Then came the question that no one in the room could avoid asking. If life this resilient, this adaptable, and this completely disconnected from sunlight exists at the bottom of Earth's ocean, what does that mean for the oceans we haven't explored yet? The ones that aren't on Earth? Because the implications of what China pulled up from Challenger Deep didn't stop at the ocean's surface. They reached all the way to the moons of Jupiter and Saturn, and they changed everything. Life is out there. For decades, the search for extraterrestrial life has been shaped by one fundamental assumption: look for water, and look for a star close enough to warm it. The habitable zone. The Goldilocks region around a sun where temperatures allow liquid water to exist on a planet's surface. It was the framework that guided telescope design, mission planning, and the entire scientific conversation about where life might exist beyond Earth. The Mariana Trench just made that framework look dangerously narrow, because what China's submersibles confirmed at 11,000 meters isn't just that life exists without sunlight. It's that life can build complex, layered, thriving ecosystems with nothing but liquid water and chemical energy. And the moment you accept that, the moment that finding sinks in two places in our solar system stop looking like frozen, lifeless moons and start looking like the most promising addresses in the universe for finding life. Europa and Enceladus. Europa is one of Jupiter's moons, and beneath its thick shell of surface ice lies a liquid water ocean estimated to be between 40 and 100 miles deep, larger by volume than all of Earth's oceans combined. You heard that right. A moon of Jupiter is holding more liquid water than every ocean, sea, and lake on Earth put together. And that ocean sits in total darkness, completely cut off from the sun, heated from below by tidal forces generated by Jupiter's immense gravitational pull, the same kind of geological energy that drives hydrothermal activity on Earth's ocean floor. The parallel to the Mariana Trench isn't poetic, it's almost exact. Enceladus, a moon of Saturn, takes it even further. In 2005, NASA's Cassini spacecraft discovered that Enceladus is actively venting plumes of water vapor and ice particles from its south pole, erupting directly from a subsurface ocean into space. When Cassini flew through those plumes, it detected hydrogen, carbon dioxide, and complex organic molecules, the chemical ingredients that on Earth sustain entire ecosystems of chemosynthetic life at the bottom of the ocean. And NASA scientists weren't subtle about what that meant. Before China's Mariana research program produced its findings, the case for life on Europa or Enceladus was compelling but theoretical. You could argue the chemistry was right, that the conditions weren't hostile enough to rule life out, but the counter-argument was always the same. We've never seen life survive without sunlight in a complex, sustained ecosystem. We have no proof that chemosynthesis alone can sustain more than microbial mats. China's samples eliminated that counter-argument entirely. Tube worms several feet long, clams, shrimp, entire food chains built on chemical energy in absolute darkness. Complex multicellular life, not just microbes, thriving in conditions that mirror what we believe exists beneath the ice of Europa and Enceladus. The biological proof of concept that astrobiologists needed and had been waiting decades for came up in a sample container from the floor of the Mariana Trench. NASA is now actively incorporating data from China's deep-sea missions into mission planning for Europa Clipper and future Enceladus exploration. The question being asked inside those planning rooms has fundamentally shifted. It's no longer, could life survive there? The question is now, what kind of life, and how do we detect it? That is not a small change. That is a complete reorientation of humanity's search for life in the universe, driven by what a Chinese submersible pulled from the bottom of the Pacific Ocean. But here's what makes this discovery hit differently than any space mission announcement or telescope image. Europa is hundreds of millions of miles away. Enceladus is even further. They are abstract, beautiful, scientifically thrilling, but abstract. The Mariana Trench is here, on Earth, accessible, and what lives there isn't a theory or a spectral reading from a distant instrument. It's real, it's alive, and it is proof, physical, biological, undeniable proof that life is far more resilient and far more widespread than science ever gave it credit for. Which makes what China's submersibles found next, in those same samples, in that same darkness, so much harder to accept. Because something else had made it to the bottom of the Mariana Trench before science did. And it didn't come from the Earth. It came from us. We already destroyed it. There is a moment when you learn what China's submersibles found at the very bottom of the Mariana Trench, where the excitement of everything that came before it turns into something else entirely. Not fear, not anger, something quieter and harder to shake the specific discomfort of realizing that humanity managed to ruin something before we even fully understood it existed. Let's set the scene. You are 11,000 meters below the surface of the Pacific Ocean. The pressure outside the submersible hull is over 15,000 pounds per square inch. The water temperature is just above freezing. No sunlight has touched this place in the entire history of the Earth. The nearest human settlement is thousands of miles away. You are in the most remote, most isolated, most inaccessible environment on the surface of this planet, a place so extreme that fewer humans have visited it than have walked on the surface of the moon. And floating in the tissue of the organisms living there inside their bodies are microplastics, not on the surface of the sediment, not drifting in the water column far above. Inside the biological tissue of creatures living at full ocean depth, in a place humanity has barely visited, in an ecosystem that evolved over millions of years in complete isolation from the surface world. China's researchers didn't go looking for microplastics. They were there to study microbial life and deep-sea ecosystems. But when they analyzed the tissue samples of organisms collected from Challenger Deep, the contamination was impossible to ignore. Plastic fibers and fragments, the microscopic debris of bottles, packaging, synthetic clothing, and industrial waste generated on the surface had traveled 11,000 meters down through the water column and entered the food chain at the very bottom of the world. And this wasn't a trace finding. This wasn't one sample from one organism that could be written off as an anomaly. It was consistent, widespread, systemic. The mechanism is brutal in its simplicity. Microplastics are neutrally buoyant. They don't float, and they don't sink quickly. They drift. They get consumed by small organisms near the surface. Those organisms die and sink. Their bodies carry the plastic downward, and the plastic gets consumed again at the next level of the food chain. Over years and decades, this process, called the biological pump, moves surface. Contamination down through the entire water column, from the sunlit surface all the way to the Haddle Zone, the deepest region of the ocean. By the time those plastics reach 11,000 meters, they have traveled further from their origin than most people travel in a lifetime. And they arrive at the bottom of the world, inside the bodies of animals that have never been touched by anything human. Think about what that actually means. The tube worms, living around hydrothermal vents at Challenger Deep, have no connection to the surface. They don't migrate. They don't travel. Their entire existence, birth, growth, reproduction, death, happens in the same dark, pressurized, chemically sustained environment, completely isolated from everything above them. They didn't go looking for plastic. The plastic found them. We sent it down, piece by microscopic piece, without ever making a decision to do so, without ever seeing the destination, without ever understanding what we were contaminating. Humanity reached the bottom of the Mariana Trench through its garbage, before it reached it through its science. And here is what makes that finding land with full weight. The microplastics discovered in Challenger Deep organisms didn't come from one country or one industry or one event that could be identified and stopped. They came from everywhere. From every coastline, every river system, every landfill positioned near water, every washing machine running a synthetic fabric cycle, every piece of single-use plastic that ever entered the ocean. The contamination at the bottom of the world is the collective output of the entire human species, and it got there silently, invisibly, while we were busy debating whether ocean pollution was really that serious. It is that serious. The deepest point on Earth just proved it. But now sit with both things at once, because this is where China's 2 decades of deep-sea exploration lands you, and it's not a comfortable place to stand. On one side, you have the most profound biological discovery in a generation. Life existing in crushing darkness, without sunlight, without any connection to the surface, thriving on chemistry alone, and in doing so, making the case that the universe is almost certainly full of life we haven't found yet. Europa's hidden ocean, Enceladus's erupting plumes. The possibility that life is not the rare, fragile exception we assumed it was, but something close to inevitable wherever the right chemistry exists. China went to the bottom of the world and came back with reason to believe we are not alone. On the other side, in the tissue of the organisms living in that same darkness, is the evidence of what we are doing to the life we already have. Not the life on distant moons, not the hypothetical microbial communities beneath alien ice, the life here, on our planet, in our ocean, at the bottom of a place so remote and so extreme that we convinced ourselves it was beyond our reach. It wasn't beyond our reach. Nothing is.